So the other day I kind of introduced these symbols, but we've got P for population proportion. And proportion, we're talking some sort of percent. Oftentimes the population proportion is simply a claim. Okay, it's just simply a claim. Hey, 50% of the population is male. That's my claim. Okay? Am I accurate? I don't know. Okay? It's a claim. Oftentimes. P hat is your sample proportion. And again, proportions are percents. So we're stepping into a percent thing. Excuse me. The unfortunate thing about P is it sort of occupies a number of different meanings in stats. We've learned it to be probability. Now it's proportion. And it's also going to be in the future p-value. So, although usually we say p-value, but it's the one letter that sort of gets multiple meanings. So you've got to be careful about the context to make sure that you know you're talking about the right p, if you will. So mu sub p hat, the average of p hats, what this is it's the mean of many sample proportions. Thank you, Asher. The mean of many sample proportions. Before I give you what that is, let me take you back to the other day, and I talked about the mean of x bar, the average of many averages. And the example I gave was I could find the average age of this class by doing it a couple different ways. I could do it by sampling, or I could do it by just asking everybody what your average age is. Since this population is fairly small, it would make sense to do it that way. But what if your population was large? And so what I suggested is, what if I found the average age of 3 people, the average age of another 3, and another 3, and another 3. And I kept taking groups of 3 until I had many, many groups of 3. And I took those averages of those groups of 3 and I averaged them. What would I get? The average age of the population, right? So keep that in mind. If I'm saying the average proportion of many samples, well, mu of p hat is simply p, the population proportion. Because we're taking many samples of the same size from the same population, and we're finding the average proportion of those samples. If I do it enough, I'm going to get the parameter. Okay. Mu of p hat is p. All right. Before we talk about sigma p hat, we have to be reminded, oh, hang on, back up a second. That's to memorize. It is, just for the fun of it, it is on the AP test notes. However, here's the thing about notes, especially if they're not your own. If you know what you're looking for, you probably don't need to look for it, right? And if you have your own notes, you know it's there and you can go, okay, I got to find this thing. But if it's somebody else's notes, how are you going to find it if you're not 100% sure what it is you're looking for, right? Does that make sense? So I don't know realistically. I know people go, oh well, the AP gives me notes. Yeah, well, we'll be looking at this very closely before you take the test, for those of you that want to take the test. But I think a lot of it probably wouldn't be all that handy. So we need to know this. The 10% rule is another one we need to know. We covered this a little bit ago in chapter 6, and it was that 10% of the population has to be bigger than your sample size, right? Or 10 times your sample has to be smaller than the population. And so this must be true to calculate sigma p hat. And what's sigma p hat? Well, that's the next thing. Now, we've learned many sigmas, many standard deviation for specific examples. And what we've learned is that we haven't really had to learn a formula or too many formulas yet, because the calculator handles the big ugly ones. But what it doesn't handle are the more advanced yet simpler ones. And that's how I would categorize this. P times 1 minus P, so the population proportion, minus 1 minus, or times 1 minus the population proportion, all over n. And that's all underneath one radical. Okay, the whole thing is under one radical. And that is one to also memorize. It is in the notes, but you want to memorize that guy too. So far, so good? So when we see percentages, this is where we need to go at this point. P hat is approximately normal if and we've learned this before too. It's definitely something to memorize. Actually, I probably should include this in that as well. N times P has to be greater than or equal to 10. Remember we did this a little bit ago? And N times 1 minus P also has to be greater than or equal to 10. So it's checking to make sure that our sample size is large enough for us to call it normal. This is the large counts condition. I don't care if you remember what it's called, as long as we know that this is how we check for normality. And just as some detail, NP, these are our expected successes. I'll put successes in quotation marks because success is sort of in the eye of the researcher. If the researcher is trying to make a better mousetrap, and the new mousetrap kills the mouse, from the researcher's perspective, that's a success. From the mouse's perspective, that's not so good, right? That's a failure. I would disagree that mice do have perspective, because if they didn't have perspective, why would they run if they see us, right?
Oh, no. The mouse doesn't have perspective till after the success.
Well, it has perspective right up until its last heartbeat. How's that? Okay? All right. So the n times 1 minus p as your expected failures. How many times will we have success versus how many times will we have failure? So if the large counts condition is satisfied, the data is approximately normal. That's what all this is about, or at least this bottom part here. Prox norm. And if it's approximately normal, you can standardize. When we standardize, that means we have to break out table A, right? Standard normal probabilities table. And that's worth mentioning yet again, that this table A works only when we know something is a normal or approximately normal, because it's the standard normal probabilities. It's the only time you can use table A. But what we've found so far is that we've been able to use it quite a lot, haven't we? And we're nowhere near being done with it. So it comes up quite a bit. So if we can standardize, then, well, next is we've got to have that new standardizing formula. So, you guys ready? Is everybody with me? Okay. So something I really haven't brought up yet, but it's something that we need to mention. Our old formula for standardizing deals with counts. Specific values. So our old standardizing formula is x minus mu divided by sigma. And I only call it old because, well, we're moving on to a different type. It doesn't mean that this one isn't any good anymore. It just depends on the situation. And that gives us our z value, and then the z we take to table A. Our new one, deals with proportions. And this one is the sample proportion, your statistic proportion, your sample, minus your population proportion, your parameter. So the x is like the p hat, the mu is like the p, divided by sigma p hat. So it's a different calculation for sigma here. That's going to give us z, and then we take that to table A like we always have. But that's probably not the best way to remember this. By the way, nowhere in the AP Stats notes is there a standardizing formula. They don't give it to you. You have to know that going in, and you have to be able to distinguish which one to use. So I would, if it were me remembering this, I would go p hat minus p over the square root of p times 1 minus p all over n. That's the guy that I want you to memorize. Okay, so let's look at a problem. let's say I claim that 20% of Idaho families hunt for their food. Okay? But I take a sample of 100 families. And that sample, when I do some calculation, I get that 24% of the families hunt. So what if I want to know what's the probability that a sample of size 100 would give me 24% or more as a number of families that hunt? So what's the probability p hat is greater than 24%? So this is probability. Not to be confused, it is confusing, not to be confused with the P up here. This is the population proportion. Okay? Probability, population proportion. I know it's the same letter, it makes it tough. I'm sorry, I didn't make it up. It is what it is. Okay. So the first thing we need to do is we need to check our conditions. Let's start with the 10% condition. Is 10% of the population bigger than the sample size? Reasonable to assume that there are more than 1,000 hunting families in Idaho. Is that a fair assumption, do you think? I think so too. So I'd say this is reasonable to assume. This is what I love about stats. In no other math class can I use the word assume. Like if you assume things in just about everything else, you're a dirty, rotten scoundrel to assume in math. But in stats, we have to make assumptions, and that's cool. Okay, so the next thing is the large counts condition. Is 100 n times p. This would be my p, right? The claim or the population proportion is 20%. So this is my big P. Is that greater than or equal to 10? Is 20% of 100 greater than or equal to 10? Yeah. If it's something that's obvious, you don't need to show me the math. If it's close, show me the math. Okay? But this one's pretty obvious. It's definitely true. But we also have to check, and is 100 times 1 minus 20%, right in the P there. Is that also greater than or equal to 10? Yeah, that's 80%. 80% of 100. It's definitely bigger than 10. So this guy says that we can find sigma p hat. This one says it's approximately normal. So we can go ahead with our calculation. So our calculation is going to be p hat minus p over the square root of p times 1 minus p all over n. So this is going to be 0.24 minus 0.20 or 0.2. So the sample minus the population or the claim divided by the square root of the claim that is because I changed the numbers from the last class. We'll see. So. Be careful with your order of operations. We'll see if we can get it in there. Ooh. I got uno. Did you get one? Yeah? Okay. Without looking at table A, could you tell me about how many or what percent of the time would I get more than 24% in a sample of 100? Yeah. No? No? When I standardize, I take that 0.20 and I put it there at 0, right? One standard deviation away here. -1 standard deviation away here. How much data fits between these two?
68%.
Good, 68%, about, right? So then how much is not in the middle? Wouldn't that be 32%? Split evenly?
Yeah.
Is? So can anybody now tell me about how often would I expect my sample size to be, or my sample proportion to be 24% or more? Correct. Let's look at it on table A anyway. It's a little different than that. It's just that, but on the stats test, you can use that. So this is going to be 1 minus. If I go here, table A, 0 is 0.8413.
Excuse me, is there a recycling bin?
There is. There's not much in it, but it's right here. Right here. No, this one right here. The colorful one. So what is that? 1587? But I would say about 16%. Thank you. About 15%, or about 16% of the time we would expect our sample to show that 24% of the families hunt. So that kind of that's a good distraction when he comes in, but it does distract a little bit. Okay.